Okay, please tell me if you still see the gray screen. Okay, thank you, it's gone. Good news for us. Yeah, if it come again, just let me know, okay? So our system has a pulley, a mass, and a spring. And we're gonna derive the equation of motion of this system. It seems like we have two possible choice to select the generalized coordinate. We may consider the vertical displacement of the mass from the equilibrium position, or we may select the angular displacement of the pulley. And the system, what happened to the system if the mass move to the positive x direction? The mass is pulling down by the force, and we assume the positive x into the downward direction. Actually, the direction of the generalized coordinate and the force don't need to be in the same direction. In this problem, the force is go downward. You also can select x to be positive in the upward direction and theta to be positive in the clockwise direction. You also can do that. And the spring will go in completion. But in this case, by the physical meaning, it seems like x cannot go into completion. No, k or the spring cannot go into like completion because we connect everything by a rule. So it seems more realistic to assume x to be positive in the downward direction. If we consider the mass m, the force that act on the mass, we select the generalized coordinate x refer to the equilibrium position of the system, and the mg of the mass is compensated with the kx of the spring. It's still not clear for you how can this be compensated, but to make this derivation simple to understand, yeah, we will ignore the mg and the static deflection of the spring first. In the next following 2 or 3 slides, we will talk about that. But okay, I don't want to ignore it without the reason. So let's assume this system is in a horizontal plane instead. So if the system is on horizontal plane, mg and the normal force that acts normal to the plane will cancel, and we won't consider the effect of the mg in this derivation, okay? So the mass m is pulled down by the force Ft, and this is the roof. The roof is under tension, and the force in the roof is go upward with the magnitude of T, which is still unknown, and we still don't know the magnitude of the force. for the pulley is supported by the pulley is supported by the force at the center. It may have Ny in vertical, Nx in horizontal direction, but everything support at the center of the pulley. And the T, tension in the cable that pull the mass upward, act on the opposite direction on the pulley. So it try to pull the pulley downward with the magnitude of T. If the pulley rotates counterclockwise with the angle theta, the geometric constraint or the geometric relationship between the theta and the x is related by the radius r. So x equal to r theta. And if the pulley is rotated counterclockwise with the angular displacement theta, on this surface will travel by 2r multiplied by theta, which is the deformation of the spring. So the spring force here, the spring force, if the spring is under tension, the spring force will go in the downward direction with the spring force of K multiplied by the linear displacement. The linear displacement is 2r multiplied by the angular displacement. So now we have the tension force and the spring force at r and at 2r. And the moment of inertia of the pulley is I. And the coordinate of this is theta. So consider the mass first. The equation, the equilibrium, the second law of Newton that apply to the mass is summation F in vertical direction is equal to MAX, and we're gonna put downward as positive. So we have Ft subtract by the tension in the roof is equal to Mx dot dot. For the pulley, it's a little more complicated if we consider the force, but we're gonna sum the moment about point O. Let's assume here is a point O at the pin location as the rotational axis. Summation M around point O is equal to IO alpha, and the counterclockwise is positive. Summation of the moment, we have the force T and the radius R in the counterclockwise, so T R is positive. The spring force on this side is downward and clockwise, so the direction is clockwise. It will be negative 2r k and theta is equal to I about the point O, or just only I, multiplied by the theta dot dot. So what we can see here, we want to derive everything into the x coordinate or into the theta coordinate is arbitrary. Yeah, in this case, yeah, we're gonna try derive in the terms of x first. So from the kinematic relationship, here we have the torque, no, the tension multiplied by radius equal to 2rk, and theta is x divided by r will equal to I theta dot dot is x dot dot divided by r. So what is T, or the tension? The tension can be the tension multiplied by r can be I x dot dot divided by r plus 2kx. So if we consider only T, or tension, we're gonna divide r throughout the equation. Did I do something wrong? T will equal to I divided by r square x dot dot plus 2k divided by r of x. Let me check T multiplied by r. Oh, yeah, I make a mistake here. This is the force. This is the force. The magnitude of the force is the spring constant multiplied by the linear displacement. The linear displacement is 2r multiplied by the theta. But if we are talking about the torque, it needs to be the force multiplied by the radius. So yeah, this is wrong. We're gonna do it again from here, okay? I'm sorry. The summation m about point O is equal to IO alpha. Counterclockwise is positive, and the tension in the cable multiplied by the radius is in the counterclockwise direction, so it's positive. But the spring force multiplied by 2r is on the clockwise direction, so it's negative. The spring force is k 2r theta multiplied by the radius 2r will equal to I theta dot dot, and yeah, TR subtract by 4r square k theta equal to I theta dot dot. So if we want to find only the tension, we can write the tension in the terms of I theta dot dot plus 4r square k theta dy by r and dy by r. Does that make sense? You move this to the right hand side and you divide the equation by r. So this is the tension in the cable. If we're gonna put the tension in the cable in here, oh, I make, wow, why it's not a good thing. Okay, I'm sorry. We want to write it in the terms of the x coordinate. We want to write it in the terms of x coordinate. So TR minus 4r squared k, and the theta is x dy by r is equal to I x dot dot dy by r. It should be like this. And the TR is equal to I x dot dot dy by r plus 4r k x. So only the tension in the cable is equal to I x dot dot dy by r squared plus 4kx. Okay, this is the tension in cable. We're gonna substitute T into this equation. So Ft subtract by T is mean I x dot dot dy by r squared subtract by 4kx equal to mx dot dot. So what we have here is mx dot dot plus I dy by r squared x dot dot plus 4kx equal to Ft. Okay, this is the equation of motion. Yeah, we took so long time for this example. I mean, it's my mistake. Actually, it's not that complicated. I hope you understand. You may try to derive it in the terms of the theta as generalized coordinate. Also, you may try to do it by yourself. Just use the geometric constraint here to transform between x and theta. And yeah, this problem is not much complicated, but require understanding of the physical phenomena. So we have a disk that roll on the surface without slipping. We have no external force applied on the system. We just have the disk that roll without slip on the surface. And the disk has mass m, radius r, and it's a thin disk. So from this knowledge, we should know that the moment of inertia about the CG of the thin disk is equal to 1/2 mr squared. And at the center of the disk is connected to a spring and a damper. So we're gonna assume a generalized coordinate as a horizontal displacement measured from the equilibrium position. So it seems like simple if the this move to the right hand side with the displacement x and with the velocity x dot to the right hand side, the force that connect to the center here, we have two forces that connect to the center. We have K, X by the spring, and another force is C, X dot by the damper. And this is on the floor. So we're gonna have the normal force and we're gonna have the mg. Do you think the friction force should go on which direction? It seems like not easy to imagine. It depends on you, but no, we have only one correct answer if we already select the direction of the generalized coordinate. But if it's easy to make you confused if you try to imagine that, wow, we have this force to the left hand side. So this thing seems like going to rotate in the counterclockwise direction, and we should have a friction force to the right hand side to make it roll without slipping. This is not a good way to consider. It's wrong. The direction of the friction should relate to the direction of the generalized coordinate that you put. So if it's positive to the right hand side, it means that the circle is rotating on the clockwise direction. And if it rolls without slipping to the clockwise direction, you should have the friction to the left hand side. So the friction is to the left hand side in this problem. And okay, by the summation of the force, it's not complicated. If you summation F in the horizontal direction equal to max and right hand side is positive, you're gonna get minus of the spring force, minus of the damping force, and and minus the friction force equal to mx dot dot. And if you consider the summation of moment about the CG, the summation of moment about the CG is equal to the moment of inertia about the CG and multiplied by the angular acceleration. And if x positive to the right hand side, the theta is positive in the clockwise direction. So if we sum the moment about the CG, mg is passed through the CG. Normal force is also passed through CG. The spring force and the damping force It's connected to CG. So it's not generate the moment about the CG. Only one force that creates the moment about the CG in the clockwise direction is the friction force, and it acts at the radius r. So it's act on the clockwise direction. So mu mg at the radius r is only one moment and equal to the I bar, or the moment of inertia about the CG, is 1/2 mr square and theta dot dot. And by the geometric constant of the rho without slipping, we can find that the x equal to theta r, x dot equal to theta dot r, and x dot dot equal to theta dot dot r. Okay, so the theta should be x dot dot divided by r square here. So we can write this into mu mg r equal to 1/2 mr square and x dot dot divided by r square. And the mu mg will equal to 1/2 r of mx dot dot. I do something wrong. Why you didn't tell me? Okay, I'm sorry. X dot dot, the theta dot dot is x dot dot divided by r, not r square. Okay. Okay. X theta dot dot is x dot dot divided by r. So here is x dot dot divided by r. So we're gonna have r on the right hand side and r on the left hand side. So finally, the mu mg, is equal to 1/2 of mx dot dot. Okay, so from here, we're gonna put the mu mg here. And what we get is we're gonna have minus kx minus cx dot minus 1/2 mx dot dot equal to mx dot dot. And finally, we have 3/2 mx dot dot plus cx dot plus kx equal to 0. So by the effect of the rotational, instead of have only one mass, we need to have additional effect of inertia due to the rotation. And the effect from the damper and the spring still be the same. And on the right hand side is 0 because in this system, we don't have additional like external force to the system. So we have only the dynamics of the system without external force. For this, we derive it through the CG. And we need to find the equilibrium of force and equilibrium of moment. Let's take the same problem, but derive the equilibrium of moment about CP. CP is the contact point here. Contact point here. The moment of inertia about the CG of the thin disk is 1/2 mr squared. If we shift the moment of inertia to about any arbitrary point, IO is equal to I bar multiplied by mr squared. It means I about any arbitrary point is equal to the I about the CG or I bar plus mr squared when R is the distance between the CG and the point O. So in this case, if we want to derive the moment of inertia about the center, the contact point instead of the CG, it will equal to ICG plus mass multiplied by the radius square. And again, if we consider the disk and draw the free body diagram again, we have normal force, we have mg, we have friction mu mg, and we have the force kx and the force cx dot as the previous page. And this is rotated clockwise. It's rotated clockwise with the angular displacement described by the theta, because this is moved to the right hand side with x and x dot. If we do summation of the moment about the contact point instead of the CG, it will equal to the moment of inertia about the contact point multiplied by the angular acceleration, and assume it's positive in the clockwise direction. The summation of moment about this point now is different from the previous derivation. In the previous page, we have only mu mg that is not x on the CG. But now we consider this point, CP, contact point, instead. So summation of the moment, we're gonna have these two forces that acts as CG and not pass through the CP and acts on the counterclockwise direction. So we're gonna have the minus kx at the radius r from this point and minus cx dot r. It will equal to the moment of inertia about the contact point, which is ICG plus mr squared, or equal to 3/2 mr square. So ICP is 3/2 mr square. And the angular acceleration is theta dot dot. We still have the geometric constraint that theta dot dot is equal to x dot dot divided by r. So what we have is minus kxr minus cx dot r is equal to 3/2 mr square and x dot dot divided by r. So this r, and if r is not 0, we can subtract all r. So finally, we can write 3/2 mx dot dot plus cx dot plus kx equal to 0, the same as the previous derivation, but this we just use only one equation to obtain one equilibrium equation, but still need the geometric constraint. So you can use the way that you like, and you can get the same result. And about the static diffraction and gravity. Before this, we have two ways to set the datum or the reference point of the xt. You can select where the xt be 0 at the free length of spring, or you can select when xt is equal to 0 at equilibrium. And in the textbook, they suggest us to select xt to be 0 at equilibrium point because they can subtract the effect of the mg and the static diffraction. So how can they do that? If this mass is in equilibrium, it means that at equilibrium point, we have the weight of the box mg, and we have the spring force, which is the spring constant multiplied by static displacement of the spring. We have this. And at this point, we set x equal to 0. If this box moves more with the coordinate x, the total spring force should be k multiplied by the x that move far from the equilibrium plus the static deflection. And the damping force will be C multiply by, maybe you can write down like d by dt of the x plus the static deflection. But the static deflection is a constant. So d by dt of the static deflection will be 0. So what you get is dx dot. You don't have this term because d by dt of the static deflection will be 0. So if you do the summation of force in the vertical direction and downward be positive, what you get is mg subtract by k x plus static deflection and subtract by c x dot. I forgot that we also have external force in the downward direction, Ft. So we need to plus the force. It will equal to mx dot dot. So what we have here, if we try to rearrange the equation, we can have mx dot dot plus cx dot and plus kx and mx dot dot plus cx dot plus kx. Okay, we may plus k multiply by static deflection and subtract by mg equal to ft. Can you follow this? We have mx dot dot on the right hand side. We move cx dot to the right hand side. We move kx to the right hand side. On the right hand side, we also move the k multiplied by the static deflection to the right hand side. So from minus be the positive, and mg to the right hand side to be negative, and ft is still on the left hand side, so it still be ft. So you know that the definition of the static equilibrium, the static displacement, the static deflection, if this is in equilibrium, the k multiplied by the static deflection is equal to mg. So this term will be 0. So this slide, the conclusion is, if you select the datum point of the generalized coordinate xt from the equilibrium position, not the free length of the spring, the effect of the mg will be cancelled with the static deflection, and you can simply obtain the mx dot dot plus cx dot plus kx equal to ft. Although this system is in the vertical arrangement, not on the horizontal plane, you don't need to concern about this, the effect of the mg. Okay, we almost done. Okay, I hope you still can survive. I also need to survive. On this slide, we are talking about the assumption of the small angle and the small displacement before this, we try to talk about like mx dot plus cx dot plus kx maybe equal to ft. You can see that all the terms, although it has second derivative or first derivative, the power of the term is only the first power. We never see the third power, the second power. We call this is a linear differential equation. But if you still remember the spring from our last class, the previous week, the spring itself need to be right in the extended polynomial terms. But we just assume that if x is more, the higher degree, no, the higher power term, the higher degree term can be assumed to be 0. So if you see this, if I ask that, can we simply neglect the nonlinear term to obtain a linear differential equation? In this case, yeah, for sure, if x is more displacement, the third power term can be ignored. For this also, the second power term can be ignored. For this, it's not the second or third power term, it's in the sine and cosine. And it's a little more complicated, and you need to carefully check like if the condition can give a small value of this or not, and you can ignore it or not. This we can, but this not sure. How about the small angle assumption? In this system, what happens if the position is deviated to the small theta and the mass is at this point? We're gonna have mg, and we're gonna have the tension in the system, and mg can be separated into two parts. We're gonna have mg cosine theta and mg sine theta. If we consider the rotating point here, and the theta is positive in the counterclockwise direction, and we're gonna derive the equation of motion. For the mass m is rotate about this rotating point, the distance from the rotating point to the mass is L. And yeah, summation of moment about point O. Summation of moment about point O is equal to the moment of inertia about point O and alpha. And by this, it seems like counterclockwise is positive. The summation of moment about point O, the mg sine theta create a clockwise moment, so it should be minus mg sine theta at a distance L. This is the moment about point O by this force. We have mg and it's separated into mg sine theta and mg cos theta. Mg cosine theta is passed through the point O, so it's not generate the moment. So the moment of inertia about point O of this single mass M should be mr square or ml square, and the theta dot dot. So what we have is ml square theta dot dot plus mgl sine theta equal to 0. The small angle assumption need to be applied to this so that we can estimate the sine of theta by the theta, so that we can have ml square theta dot dot plus mgl theta equal to 0, so that we can have a linear differential equation without the sine cosine term or the higher degree polynomial terms. Okay, the last topics for today is the equivalent system method. Before this, we know how to derive the equivalent stiffness, equivalent mass, and equivalent damping coefficient of the system. So how can we apply that thing to complicate system? We first begin with, it seems like have many parts, but the idea is we have the kinetic energy and potential energy at the initial state, at any initial state, which means that T1 should be the kinetic energy 1/2 multiplied by the mass equivalent, the equivalent mass at x dot square at time T1. This is the kinetic energy. For the potential energy, this x is also x at time T1. And this can be other source of potential energy. Can be, it may be mgh at the initial state. V0 can be something like mgh when T1. So the idea, the concept of this equation is the kinetic and potential energy at the initial state, subtract by the work done by the non-conservative force due to the damping. Non-conservative. And it always be minus because the damping force always on the opposite direction to the velocity. So this work, non-conservative work, always be negative work and dissipate the energy from the system. So this always be negative. And this term is outer external force that write in the terms of the equivalent force, and the integral will be the integral of the force and the velocity against dt. So if sometimes the force is on opposite direction with the velocity, sometimes this can give the numerical value as negative value. But by the physical meaning, we still keep the positive of this, but it can be like plus or negative something, depend on the value of the integral. And the meaning of this equation is we have the energy at the initial state. We dissipate some energy through the damper by the work due to non-conservative force from the damper. And we plus some external source work through this term. We should get the kinetic energy and potential energy from the spring at any state. And this is the potential energy at the datum. Still be the result from this side, still keep it. This is the meaning of this equation. By do the first time derivative, by doing the first time derivative, the first time derivative of the initial kinetic energy, the T1 is a constant. We can compute the value of the kinetic energy at the initial state. The potential energy at the initial state also a constant. So if we do the time derivative of constant, we can get 0, 0. And for this term, this is the time derivative of this, and this is the time derivative of this, of the force. On the right hand side, we also do the time derivative of the x dot square and of the x square. And the zero, V0, or the potential energy at reference is also a constant. So the time derivative of this also be 0. Finally, when we derive this equation, we can write a very simple equation that relates the equivalent mass of the system, equivalent damping coefficient, and equivalent stiffness in the terms of equivalent force that apply to the system. The equation is very simple. We don't need to remember this, just understand the derivation, but please keep this one for the application. What should be the useful example to use this equation? Is there any guy in this classroom try to tackle this problem by means of the free body diagram method? It's not easy to deal with. We have a lot of components in the system. We have a disc, we have a pulley, we have a mass. We may need to draw free body diagram of these 3 components and solve the multiple equations to obtain a single degree of freedom single generalized coordinate in terms of the single generalized coordinate. It's not easy. So the suggested method is the equivalent system method. We consider the kinetic energy of all the components. If we consider this one, the disk has mass m, radius rd, and yeah, the moment of inertia is id. So the kinetic energy of the disk will be the motion, the translation 1/2 mx dot square plus the rotation effect 1/2 of the moment of inertia about point D and omega square. This is the kinetic energy of the disk. How about the pulley? The pulley has the kinetic energy of 1/2 of the moment of inertia about point P and theta dot square. And the third component is the mass 2m. The kinetic energy is 1/2 multiplied by mass multiplied by the velocity. The velocity is described by the xb of this mass, and this xb is related to the x by r and 2r, which is the geometric constraint. And the kinetic energy also needs to be concerned for the spring. Do you remember if we consider the spring mass to obtain the kinetic energy when the mass of the spring cannot be ignored? Okay, the 1/2 mx dot still be the same. And the moment of inertia of the disk, the thin disk, is 1/2 mr square. Is this one. And the omega of the disk, the angular velocity for the low without slipping, is the velocity divided by the radius. So this term. For the pulley, we have the moment of inertia of the pulley and the theta dot. The theta is related to the x by the radius r. Theta is equal to x divided by r. So theta dot is x dot divided by r. This one. For the mass 2m, the velocity is xb dot. Xb dot is 2x dot. So it's this one. And for the spring, if we consider the mass of the spring mass ms, the spring mass ms, if you cannot remember, please review from our last week, the spring mass, the effect of the spring mass will be the mass of the spring divided by 3. And yeah, the velocity of the center of mass of the spring still be like 2x dot and x dot. Please check this from our previous lecture, spring mass not neglected. Okay, so if we compute this equation, we can write down in the terms of 1/2 of one huge part and x dot square. And the huge part, for example, it can be m plus this divided by the huge part here is the equivalent mass of the system. For the equivalent stiffness of the spring, we consider the potential energy of these two springs. The first spring, the potential energy is 1/2 kx squared. Simple. The second spring, also the displacement is 2x and the stiffness is k. So 1/2 k of 2x squared. So finally, the total of the potential energy is this one. So the equivalent stiffness, this one, 5k, is equivalent stiffness. To obtain the equivalent damping coefficient, we do the integral of the non-conservative force or the damping force. The damping force is minus u is equal to integral of minus cx dot dx from x1 to x2 for any damper. We do the same thing. For this first damper is cx dot directly. For the second damper, the velocity will be 2x dot instead of just x, and the d of xb will be d of the 2x. So yeah, we can obtain this form and we can compare this and this. So the equivalent damping coefficient is 5c. The simple equation here will be applied from now. M equivalent x dot dot c equivalent x dot plus k equivalent x equal to F equivalent. So here we have M equivalent, C equivalent, and K equivalent, and we don't have external force. So on the right hand side is 0. So this is the equation of motion of this system. Okay, today we have a long day and I'm not gonna teach more, but I'm gonna explain our assignment. The assignment 1, we have 5 problems and you have about 2 weeks to work on it, and you will submit it as a single PDF file on Moodle. I will add all of you in the Moodle system, and I will put this assignment again and create the submission link in the Moodle. And yeah, the problem, for the first problem here, like they give the spring stiffness and they tell the mass, and they just tell that in the equilibrium, the system deformed by 5 centimeters. They want us to estimate the stiffness of the wheel. Before this, we have the mass of the car and the spring of the suspension. and we don't consider the stiffness of the wheel. But in this case, they separate the stiffness of the suspension and the stiffness of the wheel or the tire. And yeah, you know the mass and you know the total deformation. You can find the equivalent stiffness of the series spring, but you know the stiffness of the suspension, so you should find a way to find the stiffness of the wheel. So please find the equivalent stiffness of the wheel and the equivalent stiffness of the spring in the combination. On the second problem, they have the cantilever beam, which we know the material property and the cross-sectional area property. So we should use the model to find the stiffness for the vertical displacement as a function of the stiffness in vertical displacement for the cantilever beam. And it connects with a linear spring here. You should try to imagine the cantilever beam is connect with this spring in series or in parallel, and what should be the equivalent stiffness of the system. And we have the mass. You should derive the deflection of the system. So these two problems, you mainly focus on the stiffness, equivalent stiffness, and the static deflection. And these three problems, the problem is refer from the textbook. And in the textbook, we have multiple questions, but I select only 3 questions related to these 3 pictures. In each picture, we have the degree of freedom, the generalized coordinate, x, theta, and x in vertical motion. So yeah, please use the Newton method, the free body diagram method to obtain the equation of motion. Actually, I'm not limit you only to use the Newton method. You can use the energy method, the equivalent system method, also to obtain the equation of motion. But please select only one method for each problem, the method that you feel sure to do it, to make it correct. Okay, that's all for today. You have any question? I'm gonna stop recording. If you have question, you can feel free to ask me.